Comes on everyone, let's start off. Last thing that we did a simple microscope. I have a little more on this. Let's wrap it up. Great. Now, the problem with the simple microscope, right? It gives you a magnification 1 plus d by f. But once the magnification starts increasing, because of this achromatic aberration, you start getting errors actually. The image starts it doesn't give a good magnification. So using a single lens for a magnification is really not a good idea. You can get maybe 3 to 4 times magnification, but if you want more than that, you have a problem. So we use something called a compound microscope. This is the one which you actually see in the labs. Our idea is pretty simple. What we do in this, again, terminologies are important. So we have two lenses. This is called objective piece. The one closer to the object is called objective piece. The one closer to the eye is called an eyepiece. So what's the concept behind this? We have an object. First, using the objective piece, the first one, we will magnify this thing. So we will make this bigger. Then we get a height of an image. Then this height of the image, which you're seeing, then you look through an eyepiece. So indirectly what you did, you used one lens to make the image bigger. Then you use the second lens in order to see the image. So you're actually using a lens plus a simple microscope, a combination of both. So from here, light rays will go like this, and yeah. So the observer who is here, he'll be watching this. So yeah, in terms of idea, that is the whole thing. The first lens will make the image bigger. Others, you need to keep your cams on. And the second lens is like a simple microscope. You're looking through this. So we magnify the object. This thing has a good potential of, coming in advanced paragraph or something. Objective piece. So know the derivation. The formulas are straightforward though. If you go to NCERT, they have no derivation, nothing. They just give one formula. So for mains perspective, just need to remember that. And remember, when I say mains, these things also come for bits also. So it's important. Then see the image through eyepiece, which is a simple microscope. So this is a combination of a lens plus a simple microscope. So total magnifying power will be the linear magnification of objective into angular magnification of eyepiece. What is the linear magnification? V naught by U naught. Image of the image distance by object distance into what is angular magnification? D by UE. Where did you get this D by U from? Remember, this was the derivation for simple microscope. D by U. UE meaning it is for eyepiece. So this is the simple microscope ka formula. But is the story making sense? So if you just use one lens, you will magnify. But if I use two lenses, I can make it bigger and then I can watch it. Now in this, again, we have two cases. Last time I gave you these words, normal adjustment, far point, or the near point. These things are important because they'll ask you like this only. What is the magnification of a simple microscope in normal adjustment or far point? What is the magnification of a compound microscope in near point? And if you don't know what those things mean, you will have a problem. So far point is when the image is at infinity. So whenever you keep a device in normal adjustment, your eyes are pretty relaxed. You can sit and work on it for hours without eyes getting strained. So the final image is at infinity. That means the first image which forms here must be at the focus of the second lens. So this point must be Fe. This distance will be Fe. These rays must have become parallel. That is the meaning of image at infinity. Rays are coming parallelly. This is U naught and this is V naught. Apply the formula for this thing. So 1 by F naught is equal to 1 by V naught minus 1 by minus U naught. That's your lens formula here. And the magnification is V naught by U naught. So just multiply V naught everywhere. You end up with V naught by F naught minus 1. This is the magnification of objective. Whose focal length is F naught and this is eyepiece. Whose focal length is Fe. The magnification of eyepiece is d by UE. In this case, d by UE is nothing but d by Fe. Therefore, the total magnification will be magnification of objective into magnification of eyepiece, which is V naught by F naught minus 1 into d by Fe. The length of the microscope, that is the distance between the two lenses, is called length of the microscope. That is one more. Is V naught plus Fe. So distance between the lenses is called length of the microscope. This is the actual formula for normal adjustment. But if you go to NCRT, they don't have anything like this. They did a lot of approximations. But look at how we derived it. That's the main important there. I just used lens ka formula, nothing much. All clear with the steps. Now what these NCRT people did was this. Magnification is V naught by F naught minus 1. And you have one very good question here, which you need to remember, d by Fe. Now, if you want to increase the magnification, what should happen to the focal length? Both the focal lengths must be small because they're in denominator here. So for more magnification, F naught and Fe must be small. This itself is a question. In a simple microscope, for more magnification, which of the following is true? F naught is big, Fe is small, both are big as options. Because F naught is very small, V naught by F naught minus 1 can be written approximately equal to V naught by F naught. And length of the microscope, which is V naught plus Fe, because Fe is very small, you can write this thing as approximately as V naught. These are the two approximations NCRT took since Fe is small. Now your formula becomes magnification is equal to, so V naught by F naught minus 1 become V naught by F naught, that became L by F naught D by Fe. There. This is a result you should remember. This is the compound magnification of compound microscope for normal adjustment. Direct questions in the exam. The length of a microscope is 10 centimeters. The focal lengths are 5 centimeters and 6 centimeters. Find the magnification of a compound microscope. First ho gaya question. And even if you try to derive, the problem is you will end up with this formula. You won't understand how the hell did you get L from. So this is a formula which is there in NCERT directly. So they didn't give any derivation, nothing. This is the formula they have. So the derivation is important for they could ask somewhat in advance in some other way, like a paragraph, but for a means and bits thing, you just need to know this formula. Here, L is the length of the microscope. All clear with this? Next thing. Now, in this, there is that case 2. Now, this generally they won't ask you in mains or bits, but they could frame it in, like I said, near point. What if the image is forming at D? So the final image is forming at the distance of least vision, meaning your eyes are maximum strained. So you always have to work from back. So this is F naught, this is Fe. So this was your object. You get an image. So these light rays, when they go like this, and when you extend them backward, this is your final image. And that image should form at a distance d from the back. That's the meaning of it. Same story. So this would be your UE. Apply the formula. 1 by VE minus 1 by UE is 1 by FE. Then multiply D everywhere. So VE will be minus D, minus 1 by UE is 1 by FE. Minus 1 by FE minus 1 by D. Remember the magnification of eyepiece? D by U. So you end up with minus 1 plus D by FE. This is your magnification of eyepiece. The total magnification is M naught into M eyepiece, and this is V naught by U naught into 1 plus D by FE. And the length of the microscope here is V naught plus UE. Sorry, this is VE. This was UE. This was V naught. So the length of the microscope is V naught plus UV. That's it. In this, there is no shortcut and all. This is not there in NCERT. But they can ask. So the near point case, because in simple microscope, you have a near point. Compound microscope, they can frame. Clear with this? That's the formula for the simple microscope. So these are the main things here. F naught and Fe must be small. This they asked multiple times. Magnification is L D by F naught Fe. D ka value is 25 centimeters. L is they will give you, F naught Fe they'll give you, they'll ask for magnification. You know the formula, it will take 30 seconds. You don't know, you leave the question. So you're gone. And again, I'm telling you, they specifically mentioned, because these topics, right, we used to ignore a lot even before 2021, 2022. Then JE people gave a thing. We have optical instruments, dispersion, semiconductors, diffraction, polarization, bar magnets. So there are a few topics like this. It's like inorganic physics. Tatta marna hai. There is no other way. And they have specifically mentioned in mains, they'll give 10% from these chapters. That is roughly 2 to 3 questions. Right. So, like I told you, right, I used to teach this at the end of the portion, and your seniors used to ignore this royally because किसी को मजा नहीं आता था. मुझे भी मजा नहीं आता है, but there is no option. 2 to 3 questions is not a joke. Right. 4 marks will push your rank by 1,000, 2,000. 12 marks is like you're gone. So that's why we have to do all this stuff. So the reason now I'm doing it a little early, because now whatever exams I'll conduct, I'll push these questions in every exam, which you will not remember anyway, that's for sure. But after messing up the paper, then you'll go and revise. So there is a good chance you'll remember. So that's the game I'm trying to play. So let's see if it works. And anyways, so we are spreading it out. So that's about the compound microscope. And the last thing is a telescope. So telescope. So what is the difference between a microscope and a telescope? The end of the day, the story is always about looking at angles. In a microscope, the object is so small, the angle subtended is very small. So we need to make the angle big. In a telescope, the object is already big, but it is so far, the angle is very small. Like for example, sun is huge, but the distance is so far, the angle subtended is very small. So in a telescope, we observe distant objects. So objects are at infinity. So that's one advantage. So light rays are coming parallelly. Again, we have two lenses, objective and eyepiece. Now, since the rays are coming from infinity, they will meet at this focus here. So this distance here will be f naught. Now, if you take a normal adjustment, so these light rays should again hit this lens and they should again become parallel. Again, when you want to look at something very far, you want your eyes to be relaxed so that you can observe that in the space for as long as possible. Normal adjustment. So interestingly, so this distance becomes Fe. And here, this is your height of the image. So here the angles are leaving at beta. Here the light rays are coming at an angle alpha. So tan alpha is approximately alpha, which is hi by f naught. Tan beta is approximately beta, which is hi by fe. That's the thing there. So here the magnification is the angle you would have seen without the instrument with the instrument. So beta by alpha, we end up with minus f naught by fe. Minus sign because for this guy the focal length is positive. For that guy we're taking fe backwards. So minus simply indicates image is inverted. This is the magnification and length of the microscope is f naught plus fe. There, these are the main results. Easy to remember. So in this primarily have only normal adjustment in NCRT. In most cases, you only normal adjustment. Only in simple microscope you have that far point. The second case is this. The image will form at the distance of least vision. We again play the same story there. We will say these light rays are meeting here at hi, this is V, then we do a little working there. So that's a formula you need to remember. So I'll just put it down there. So the magnification of a telescope, M is given by minus f naught by fe. So f must be large, fe must be small. Did you see the difference? So people get confused here. So for a compound, both should be small. Length of the microscope is f naught plus fe. There. This is the main thing you need to remember. But clear with the process, a little understanding of a derivation helps. So rays are coming parallelly, rays are coming out parallelly. So they will meet at that point is a common focus for both of them. Let me show you how they'll frame questions on this. Look at this. Just read the question, take a minute to solve, and then look at the answer. So if you look at the first one, a small telescope has an objective focal length, so this is f naught. Eyepiece का focal length is fe. He's asking what is the magnifying power? Minus f naught by fe. Direct formula. What is the separation between the objects? F naught plus fe. When the final image is formed at infinity, meaning he's talking about normal adjustment. बस हो गया question इतना ही था. That's it. If you just know this formula, you're done. That's a proper mains question. See the next one. Next one is little better. You have a little more working to do. Take a minute, give it a try. Let's see the second one. So diameter of the moon is 3.5 into 10 power 3 kilometers. Its distance from the earth is 3.8 into 10 power 5 kilometers. Fair enough. It is seen with a telescope whose objective and eyepiece are 4 meters and 10 centimeter. Can you see that difference here? F naught is pretty large. What will be the angular magnification of the image? First thing we found the magnification. F naught by Fe, we got 40. So that means whatever angle you can see normally with your eye, you can make it 40 times bigger. So when you see with a normal eye, what do you actually see? So if this was the moon, this was the diameter, let's call it small d, and you're looking far away from the earth. So this is your angle which you can see. Since the distances are pretty small, you can write theta is equal to 3.5 into 10 power 3 by 3.8 into 10 power 5 kilometers. So this is what they calculated, 0.009 radians. So this is the angle you would see without any instrument. Now, when you use a telescope, it magnifies 40 times more. It magnifies the angle. So magnification into visual angle. So that is 21 degrees. Making sense how it worked? Because the number is very small, you can almost treat it like an arc length. Sine theta becomes theta and all that stuff. Any doubts on this? There, you're just playing with that one formula there. Let's just see one more question. This is a good one. The second one is a good one. That is a kind of a question they can frame in maybe in advance, but have a look at this. So if you look at the first one, right? The first one is again straightforward. Telescope consisting of an objective focal length. This is f naught. Single lens. This is fe. Divide them, and then he's saying is focused at a distant object. The parallel image from the eyepiece. It subtends an angle of 2 degrees at the objective, Means without anything, if you look at this, you are seeing 2 degrees. So he's asking what is the angle of fringe width? So magnification into the angle. So direct, straightforward, same as the previous one. This thing here, they gave the angle also. Look at this one. The next one is a big one. The focal length of an object when the eyepiece or astronomical telescope are 60 and 5. So this is f naught and this is f. Great. Calculate the magnifier and the length of the telescope when the final image is at infinity. So this guy is normal adjustment, which we derived. Or near point. Whose formula we know? Magnification is f naught by fe and length is f naught plus fe. Direct answer. You're done. The second one, distance of vision, this is your near point. Sorry, this is the far point. This is your near point. Means in this case, the observer thinks the image is at capital D. So this is how the picture looks. And so remembering the formula, if you can derive it, that will be easy to remember. So one thing is clear, rays are coming still from infinity only. So this distance is still f naught. And the rays are going from here. This is where the image forms. HI, the final image. And you're saying this distance here. So this would be your UE, and this distance would be your VE, which is minus T. That was the idea there. Hope that is making sense. And then we get the formula. So magnification is f naught. But same story again. If you look at this angle here, this angle was alpha, this angle was beta. We do the same thing again. So tan alpha is approximately alpha, which is this h by f naught, and tan beta is approximately beta, which is h by that angle UE. So magnification is beta by alpha will be f naught by UE. Previously that UE used to become FE. Now you got UE there. And then we can use the Lenska formula. 1 by VE minus 1 by UE is equal to 1 by FE. This is 1 minus D, 1 by UE is 1 by FE. Multiply with f naught, so magnification would be f naught by UE. Substitute here, so this will be f naught. This is also backward, so that is also minus actually. UV is also backward, so that's a minus sign. So this would be how much? One plus FE by 1 plus D. Remove FE common. You end up with 1 plus FE by D. This is the magnification for far point. So yeah, that's a little working there. Just understand that whenever there's a far point, the final image forms at D. So using that, you have to find UE and then you have to go back to the story. This is not there for mains. Like they is not there in NCRT. I don't think they'll expect you to do this in NCRT. Mains may. Advance is a different story though. They can always explain a small story and this is a microscope and you're done. So they can start asking. Clear with the stuff. If you can handle this level of questions, it's at least the previous 3 questions, right? I think you're ready with this. The last thing, just the differences there. We put down this table. This is a good one. It has all the things summarized. What's the difference between a compound microscope and an astronomical telescope? It increases the visual angle of near tiny objects. It increases the visual angle of distant large objects. So the reason is different. So here both are convergent differences. I think this fourth point is the most important one. Fourth and the fifth. So magnification is this LD by F naught by FE, and magnification is F naught by FE. Here you have to magnification is increased by decreasing the focal length of both the lenses. Here you have to increase the focal length of objective and decrease the focal length of eyepiece. RP is called resolving power. This is removed from the portion, so we don't need this. So fourth and the fifth point are the important ones. So go through the top ones. And one last thing, we have something called reflecting telescope. We don't have any questions on this. It's just a theory. So when you actually go to this Hubble telescope and all this stuff, these things, right, they need to collect a lot of light because the light that is coming from space is very dim. So when you look at this Hubble telescope and all, which work, they're focused at one point in the space for weeks. 10, 15 days, they're just looking at one point. They take millions of photographs and then they overlap all the photographs. They literally collect pixels, each pixel from each photograph, and they generate a whole new thing. So you need to be able to collect a lot of light. So using a lens is a bad idea because you'll get chromatic aberration and everything. Using a spherical mirror is also a bad idea because you get a spherical aberration. So we create a parabolic mirror because a parabola, a property, right? If light rays hit the parabolic mirror, they meet at the focus. There is no error in that. Expensive. So that's why you, but it is fine. It is worth it. Like, if you're making something so precise, cost is not a problem. So we make a big parabolic mirror. We have one spherical mirror, a secondary mirror. And we have a lens here. So the idea, this is how it works. The light rays are coming from infinity. They will all try to go and meet at the focus. So you can make this thing aperture really big. Meaning, if you can literally play football in that thing, like those are such big things there. We have a so this is a parallel beam. So we want to collect as much light as possible. So we need to make this really big. And once you hit here, these things will bounce and they will go through the lens. And this is your eyepiece. And then we use this light to do whatever it is. So this parabolic mirror is called objective mirror. Remember objective lens and eyepiece? So we don't have an objective lens, we have an objective mirror, which collects all the light rays and then sends it through a secondary mirror, which will send it through a lens. So that's it. So we don't have anything more than this except this one concept called reflecting telescope. So not sure how they'll frame a question or anything. Just have an idea. This is called a reflecting telescope. These are the things which are actually used for all these observatories. Clear? So if you see how many formulas we had, so here we have two formulas for telescope, compound microscope, another two formulas, length and magnification, simple microscope, another two formulas, d by f and 1 plus 2 by f, that is 6. Chromatic combination, this is two formulas, 8. This thing is, yeah, you can derive this, but 9, 10. Yeah, maybe you can count these things instead of those two, so still 10. And then Cauchy's formula, just remember it. 11, 12, 13, 14, 15, 16, 17. It's a concept, like, but yeah, 18, 19, 20, Newton's length formula, 21, 22, 23, you need to remember this, 24. This thing is not a main thing, but yeah. These things you can differentiate and derive them. 26, 27, 28, 29. Yeah, I think by the time I count everything, I think you'll easily hit around 35, 36 questions, 36 formulas there. So there. The problem with the chapter is that you need to remember all this stuff and you need to know the sign convention. If you know these two 70 to 80% chapters in your hands, there's still more variety. We can keep playing more and more, but you have an idea now. You can handle most of the things with what you know. The advanced sheet I sent you is a good one. Do give it a try. That should take care of most of the things. And with that, we have finished ray optics completely. So I didn't keep any pending there. Next thing is waves. Waves is another good chapter. Again, here also, right? Little, this thing also has a lot of standard models. So as long as you know the standard models and you actually understand what is happening, the chapter is fine. So before jumping into the waves, so when you keep saying waves, exactly what are we talking about? So we need to define something first. Disturbance. So what is a disturbance? Technically, imagine this thing, right? Everyone is sitting in the class silently and you suddenly start shouting. Teacher comes and say, why are you disturbing the class, right? Same thing. Let's say all of you went to a party. Everyone is jumping and dancing and you're sitting quietly. The person will come and ask, why are you so quiet? Did you see the problem? So is shouting a disturbance or being quiet a disturbance? What was the problem? The problem is not that you're quiet or you're shouting. It is always comparison with respect to the surroundings. When everyone is quiet, you're not quiet. You are, the odd one out there. So the disturbance is simply defined as it is a change in property with respect to surroundings. Now, that property can be anything. Example, if a bulb is flickering in a room, that's a disturbance. A student shouting in the class is a disturbance. So when the bulb is flickering in a room, what is the property that is changing? Intensity of light. So that's the definition of a disturbance. So here the property that changes is intensity of light. Now this property, right, which changes can be anything. It can be displacement, it can be electric field, it can be magnetic field, it can be pressure, density. It's just a property. It could be anything. The property can be pressure, displacement, electric and magnetic fields, and so on. So if a particular property is changing with respect to time, with respect to surroundings, we say it is a thing. If I take an example, let's say we take a string and you send a wave pulse. So as this pulse is traveling forward, observe a point here, A. This bump will travel here. This bump will be somewhat like this, and this bump is gone here. If you look at Eka motion here, so look at A here. A is initially on the horizontal surface, then A has gone little up, then A has gone to the highest point, then A has come back to the bottommost point. So what is changing here? What property of A is changing here? The displacement of A, isn't it? So when a wave pulse goes on a string, the property that changes is the displacement of point A. That is the first thing. So disturbance is simply a change in property with respect to the surroundings. All clear with that definition? The property could be anything. So what is a wave? So wave is the propagation of this disturbance. So in your class, let's say the person in the first bench started shouting, ah, karke. Then he keeps quiet, the second bench shouts. Then they keep quiet, third bench shouts. Then they keep quiet, fourth bench shouts. How does this look like? It feels as if this disturbance is traveling, isn't it? So that is the meaning of propagation of a disturbance. Disturbance is you are messing up the whole thing. And now you stop and the other guy starts doing it. So it feels like it is moved on. So the propagation of disturbance is called a wave. Meaning a simpler example, when you're standing in a line and someone pushes you from the back, what happens to you? You push the guy in front of you and you come back to the same position. That guy pushes the guy in front of you, he comes back to the same position. It is like a dominoes, right? The whole thing starts falling. So it is propagating, the disturbance is propagating. So propagation of a disturbance is called a wave. You can also define wave in terms of energy. So in a wave, energy and momentum are transferred without the transfer of material. If you ever been to the gym and in that there is something called a battle rope, ever did that exercise? So they have a thick rope there and you're just swinging it up and down. You get really tired. So why do you get tired? Because it is pulling out energy from you. So now waves can be classified based on the medium into two types: mechanical waves and non-mechanical waves. So mechanical waves require medium to propagate, like sound, waves on a string. They require medium. Without medium, they won't travel. Sound cannot travel in vacuum. If you take electromagnetic waves, they don't require medium to propagate. Light comes from Earth to Sun to Earth, travels 15 kilometers, and there is nothing there. Not require medium. Example, electromagnetic waves. We have a separate chapter for it. So that is one way to classify based on the whether you require medium or you don't require medium. Now, there is another way you can classify this. Waves can also be classified based on the propagation of the particles or the motion of the particles. Or you can say the direction which the property changes. That becomes more technical. I'll just keep it simple. The first thing is a transverse wave. So in a transverse wave, the particles oscillate or the property oscillates. Now, when I say property, maybe it is an electric field or magnetic field. It is changing direction in that way. Oscillates perpendicular to the wave propagation. The best example is the waves on a string. So this was the pulse here. And I'll just copy this example here. Look at this thing here. How is A moving when the wave is going forward? So here the wave is going forward, but look at how wave is going forward. Look at how A is moving. A is simply going up and down. So here A goes up and down. A actually never goes front and back. So that means if you're stranded in the middle of an ocean without wind, even if there are waves, and if you sit in a boat, the boat is not going to go anywhere. You'll be stuck at one place going up and down. So generally movies may they show, right? You just drift. It is not true. If there is some wind or if there's a shore nearby, fine, you're lucky, or else you're gone. So the wave goes forward. So in a beach, right, the waves which you see are actually transverse waves. The particles go up and down. This is the propagation of this thing. But the wave is going forward. Tsunami is a transverse wave. So when there is a tsunami, what are the safest places to be? First safest place, if you can have a mountain or something very tall, climb on it. The second thing, go into the sea. They're the second safest place. Because you need to understand how waves are generated. What happens in a wave, right? Generally, I'm just exaggerating, you have a wave like this. Nothing actually happens to the wave. So the wave is just there, right? It is just traveling. Now, what happens is, as this wave comes to the coastline, if you ever go to a place like Goa, right, the beaches are like this. It's pretty shallow. Matlab, you can just walk inside for a kilometer or 2 kilometers, and the water level is 4 to 5 meters deep. So these places are very good for beaches. Like Goa is one good example. But if you go to beaches in Kerala, right, the beaches are like this 10 meters, and there's a huge cliff. This is a very bad place for beach. People die. But these are very good places for ports. You can bring ships very close to the coastline. So if you see, Kerala has 2 to 3 ports. So these places are very good for shipbuilding and stuff. Bringing your ports. These are good for beach and all activities. Now what happens? Now as the wave is traveling and coming towards the coastline, the front part of the wave will hit the ground here. Once it hits the ground, the front part actually slows down, and the back part is still going with the same speed. So the back of the wave starts climbing the front part of the wave. So the wave height actually starts increasing. So as the wave goes inside, the front part slows down, and the back part is climbing the wave. At some point, you reach a certain height. So there is a calculation for this. The height of this will be around 0.67 times or zero point 0.7 times the wavelength. So the longer the wave, the higher you get before it breaks. And then this thing just crashes and you get that beach color wave kind of thing. So generally in a beach, the wave ka size is around 2 to 3 meters of width or 3 to 4 meters maximum hota hai. A tsunami ka wavelength is around 10 kilometers. It's huge. Getting it? Because tsunamis come during an earthquake. In an earthquake, right? Literally the continental plates, if you know how it goes, so if you have a continental plates which are going like this. So this continental plate is getting pushed under this. It goes inside, it is melting there and generates a lot of pressure. One fine day, this thing will just get up, just pushes up. And this is huge. We are talking at a continental level. The kind of wave generated energy released is immense. And that wave pushes on every direction. Now in a tsunami, what happens now? Imagine that wave comes and hits the ground. This thing is almost traveling with a speed of around 600 to 700 kilometers per hour. When it hits the coastline, it reaches a height of around 100, 200 feet, almost 10 to 15 floors height. And it rushes into the coastline. It pushes almost 2 to 3 kilometers into the city. So if there is a tsunami in Arabian Sea, Mumbai won't be there. Water will start from Western line and cross the Eastern line and go to Navi Mumbai. So yeah, it's a bad place to be. But luckily, we don't have any earthquake zones in Arabia. If you want to get a tsunami still, the only way it is a meteor should come and fall in Arabian Sea. And then we get a big splash and then we can get a tsunami. So that is the only possibility there. In 2004, right, I was still studying then in college. There was a big tsunami in Indonesia, one of the biggest one. That tsunami, right, imagine it started in Indonesia. It reached Chennai in 4 hours. And no one knew it was coming. The first people to recognize was in Andaman में the Indian Navy, right? They realized something was wrong and they sent a signal. It took 1 hour to go from Andaman to Chennai. They didn't have enough time to evacuate and everything. They tried their best, but literally Chennai mein, if you see all the coastal towns below Chennai, right? Literally they got wiped out. Nothing left. There was a town, next day there was nothing there. There was just sand and that's it. Nothing was there. So wiped. It was horrible there. We collected funds and everything and gave it like kind of things. It was bad. So that way. Now, why did I say going into the sea is better? So this actually happened. So I think in Japan or somewhere there was a big tsunami there. Another problem kya hai na? If you just leave, if you are a fisherman and if you leave your boat in the coastline and go, the tsunami will hit this boat and will take into the land. It will get destroyed. That is your whole life, right? Like that is where what you're surviving on. Another idea is this: when you know the tsunami is coming, you take your boat and go into the tsunami. Now what happens? If you just stay here, what did I just say? It's a transverse wave, isn't it? The boat simply goes up and down. So as the wave comes, the boat climbs the tsunami. As the wave goes down, boat comes down the tsunami. And the tsunami is so large, almost 10 kilometers, you don't even realize you're on top of a tsunami. Only while climbing and getting down, you'll feel little jerk, but rest of the journey will be quite comfortable. The tsunami is just going below your boat. So if you want to save your boat, you have to go into the tsunami. If you don't have a boat, better you be on the land. What if you drown? So you're in a boat, Nari. Don't drown, you're a fisherman. Anyway, so we can't stop a tsunami, but we can have detection systems. So did you ever see these buoys in beach? So what these people do now, we have these buoys there. So you place them something like, every 500 meters or 1 kilometer with GPS tracker. So when the tsunami comes, this thing rises up. Your GPS tracker will suddenly switch on. You might think, okay, it does an error. Within few seconds, this thing rises up. Within few seconds, this thing rises up. Now you know something is going on. And after some time, this also rises up. After some time, this rises up and this thing comes down. Now you have figured out the wavelength of the tsunami, isn't it? And you figured out at what speed it is traveling. You can at least send a warning signal. Now, if you know tsunami is coming in 3-4 hours, you can at least evacuate. There's no way to stop it. All you can do is run. So you need time. So that's a bit of a transverse wave. So tsunami is a transverse wave. The next thing is a longitudinal wave. So in a longitudinal wave, the particles oscillate in the direction of propagation. The best example, right? When you're standing in a queue and someone pushes you from the back, you're also going front and back. And the disturbance or the domino thing is also going front, isn't it? You're traveling in the same direction. Best example is sound. Sound is a longitudinal wave. Think of like this: when there is no sound, the molecules are equally spaced, and just drawing lines for understanding. Now, when a sound propagates through this region, so there are certain places the particles come here, they will expand at some places, they'll compress at some places. Compressions and rarefactions. So here, if the wave is going in this direction, the particles are also oscillating in the same direction. So they're just going front and back about that point. Just give me a minute. My system just crashed. I'm not sure what happened with this desktop. Let's take a break. Now, come back by 9:35. My PC just crashed. I'll just restart it. Take a break. Come back by 9:35. This will take another 4 5 minutes to start. Yeah, comes on everyone. So look at this.
I just want to show you a demonstration of transverse longitudinal waves using Slinky. So that's the same with longitudinal waves as well. The energies of Slinky is what the waves. Direction.
Able to see this? Okay. So let's see this thing. So that's a slinky, I'm sure. You must have seen this before. So if you take the slinky here and see, when he's sending a wave like this, can you see it's going up and down, but the wave is going forward. So this is a transverse wave. I think it's lagging a bit. Now, if you push it front and back, can you see that bumps there? So that thing, right? So that it's getting compressions and expansion, compressions and expansion. So that's your longitudinal wave. So the wave is going forward. The particles are also getting compressed and elongated in the forward direction.
And these pulses move along in the same direction that the energy is flowing. So that's a longitudinal wave.
That's your transfer. So I'll do post this in the group. So let me show you one more.
We have here.
Yeah, this is standing waves. There. You will get this in Amazon for 300, 400 rupees. I do have one. Interesting stuff. But there, he fixed one end and they were giving. Can you see how the wave is there? Now, just observe any one particle. Huh? It's not going front and back. It is just going up and down. So look at that particle, the arrow there. If you see that point, right, it's almost going up and down. It is never going front and back. This is a transverse wave if you do this way. But if you push it front and back, you're going to get a longitudinal wave. This is another good one. Look at this. This is another way to generate a wave. Why is this? Yeah. This is a wave pool. So you can see at the back, there are white color kind of things. Those things, right? You can push it forward, you can push it backward, you can keep moving them. You can generate a wave. I think there is a lag. So there is a wave being generated from all directions. They're coming and meeting at the center. You can't see the wave. Can you see? It doesn't look like nothing is there, but there is a wave there which is coming. Now see, it is moving. So once it all meet, can you see just how did it splash? Once all the waves meet, it just splashes on the center. It's coming for all of you, or it is lagging for most of you? Anyone can say something? Yeah, it's lagging a lot. Okay. So that is one. You can have a lot of waves. So this is a wave in real life. Tacoma Bridge. If you ever heard about it.
As you can see, this bridge was exceptionally long and narrow, over half a mile long, only 39 feet wide.
So later we'll talk about this thing. It's called resonance.
On November 7th, the bridge suddenly went into a twisting motion. The wind speed was a steady 42 miles per hour. This was enough to keep the bridge oscillating in one of its natural modes of vibration with a period of 5 seconds.
Can you see that bridge? So the whole bridge is vibrating. So there's a phenomenon called resonance. So we'll see that later on. Yeah. So yeah, I think there is a lag. But okay, we got a rough idea there. These videos are lagging nowadays. The geocast speed has gone down, I guess. I'm not sure why. Anyway, so but I hope everyone is clear a bit about what is a transverse and what is a longitudinal wave. All clear with that stuff? That's important. Like, because I can write all the equations and everything, but you should start feeling like, oh, aisa hota hai transverse wave. That idea is important. Great. So there. So you can classify waves in terms of mechanical and non-mechanical, or transverse and non-transverse wave. Longitudinal wave. The next thing, whenever you want to study a wave, you need three quantities. If you know these three quantities, you know everything about the wave. You know all the information that you need. So there are three quantities required to study a wave. The first thing is frequency. We use the symbol F. So what is frequency? We did this in SHM, same thing, number of oscillations per second. Or number of waves per second. The frequency, it does not depend on the medium, it depends only on the source. So if you send a sound wave from one medium to another medium, the frequency doesn't change. What changes is the wavelength and the wave speed. So, and this is independent of medium. One of the most common device we use to generate frequency is a tuning fork. So a tuning fork, right, it generates constant frequency. Whether you hit it gently or whether you hit it hard, it always gives you the same frequency. How does a tuning fork look like? I'm sure you must have seen in the lab. This is how a tuning fork looks like. So if you take these two ends as A and B, these are called prongs. These are the prongs of a tuning fork. So frequency is F. Now when you hit this tuning fork, you know how these things move? A and B, if you look at them, they both of them go away at the same time, and both of them come towards the mean position at the same time. So if you try to write the displacement, XA will be A sine omega t plus pi because it's going backward. XB will be A sine omega t. So both the prongs will be out of phase by 180 degrees. So both are going away, both are coming towards at the same time. A and B are out of phase by pi. That's a good theoretical question there. So the prongs of a tuning fork are out of phase by what? Are they in sync? They're not in sync. So when A is coming in, B is also coming this way. So either both will come inside or both will go away from the mean position there. It is based on the material there. I mean, that is how it is. I'll not get into the construction part. That's an interesting thing though. But so, and how do you change the frequency of a tuning fork? There are ways to change the tuning fork of frequency. You can add weights. By adding weight to the tuning fork, you can change the frequency. So if you put some wax or if you attach some weight, frequency changes. It decreases. By adding weights, frequency decreases. Or if you increase the temperature, the prongs will expand. It becomes more difficult to oscillate. The frequency again decreases. So by changing temperature or by adding weights, you can mess up the frequency. If temperature increases, frequency decreases. Clear with this? And how do you generate waves using a tuning fork? Case one, let's say you keep a tuning fork like this, horizontally, and you connect a string. So initially this point is here. This is t is equal to 0. The time period t is 1 by f. So this is the time taken for one oscillation. So when the time is t by 4, this particle has gone to the extreme position. T is equal to t by 4, you're at extreme position. The wave will look like this. The string will become like this. When the time is t is equal to t by 2, this particle will come back to the mean position. You have created an half loop. When the time is 3t by 4, remember, so this point is simply going up and down. You would look something of this sort. When the time is capital T, you come back to the mean position. you have completed a wave. So you have created one full pulse. So the wave is continuously moving forward. So basically, in one oscillation of the tuning fork, you get one wave. So frequency of the wave is the frequency of the tuning fork. This is how generally we connect the wire or whatever. But there is another way you can keep a tuning fork. All clear with this page? Case 2, what if you keep the tuning fork vertically? This is t is equal to 0. This is the string. So when time t is equal to t by 4, this guy will go front. So the moment it goes ahead, you actually get an half loop directly here. So the moment it pushes forward, the string becomes slack. We get an half loop. So here it was at mean. Here it has gone to extreme. So once you push forward, you get an half loop there. And when the time becomes t by 2, you again pull it back suddenly there. I'm not drawing it clearly, but you actually get a full loop. Then when you do 3t by 4, now you go inside. So you get something like, so again, you're going to the mean, but you're going backward. You're going mean, you're going forward. You are again at the other extreme. See, understand, as the wave is generated, the wave will keep going forward. Wave will not stay there. It is going forward and you're generating continuously. So once the wave goes forward, that string again becomes kind of like flat only. So, and you're pushing it continuously. At t is equal to t, again, when you push forward, this thing I'm actually unable to draw properly, you get again a bump. You actually get two pulses. So this is a good one. Like they can trap you like this. So in one oscillation, we get two pulses. If they don't mention anything, it is case 1. If they specifically mention case 2, you're gone. The frequency is double. In one oscillation, we get two pulses. So frequency of the wave is 2 times the frequency of the tuning fork. Clear with this? So if nothing is mentioned, take this case. Everyone clear with the frequency. So this is your first property. So you need to know the frequency for a wave. So this gives you one information. The second property, wave speed. We kept on saying wave propagation, but how fast it is going. So what is wave speed? The speed at which the wave propagates or the disturbance propagates. So when you're standing in a line and when you push the guy in front of you, it's like the domino thing. Like how fast is the next guy going to move? So, or if you're seeing this line from far, right, you can see people falling one after another. So that is different from a particle speed. So the wave speed is independent of the source. It depends only on the medium. Means whether I shout or you shout, speed of sound is not going to change. Speed of sound or speed of a wave depends only on the medium. Frequency dependent on the source, it is independent of the medium. So they are different and depends on the medium. The sound wave always goes with the same speed, doesn't matter who shouts. So one thing you have to be very clear in this. So when the wave is traveling, if you look at any particle A here, A is always going up and down in a transverse wave. So this is the speed of A. A is going up. This is called particle speed. So particle speed is different, wave speed is different. Both are two different things. Don't get confused. There is a relation between them, but they're not the same. The wave speed is the speed at which this disturbance is propagating. Particle speed is individually what are the speed of the particles. This is the second property. The third one, the amplitude. Again, same definition from SHM, the maximum displacement from the mean position. This depends on the medium and the source. It depends on both. So when a wave goes from A to water, its amplitude does get messed up. It also depends on the source. Depends on source and depends on medium. So frequency does not depend on medium, right? Sound speed of the wave depends on the medium. Amplitude depends on both the things. So if you have a rod like this and if it is oscillating up and down, this is your amplitude. We are taking this as a string. It's like the battle rope thing. You take a string and you're pushing it up and down. So these are the three properties you need. If you know these three properties, you know everything about the wave. Favor this? So again, just to brief up everything, what was a wave? It is a propagation of disturbance. What is a disturbance? It is a change in property with respect to surroundings. Waves can be classified into mechanical, non-mechanical. Require medium does not require medium. You can also classify them in transverse and longitudinal wave, right? So if you see waves on a string are transverse and mechanical. Sound waves are longitudinal and mechanical. Light is a transverse wave but non-mechanical. So you can have both the classifications differently. And then we have three properties: frequency, wave speed, and amplitude. The next thing. So that is all theoretical part of it. So how do you represent a wave mathematically? So that's where we get a wave equation. So the idea is here. Remember we said let's take y. What is y? Again, y is not the y coordinate. It is a property. This can be displacement, pressure, electric field, magnetic field, density, anything. So this is a property. Y is any property that is changing. So let's say there is a disturbance. So this is y versus x. So this is a graph basically. Simplest example, think of like, this is a pulse on a string. Like there is a rubber band which is tied between 2 points and you pulled the rubber band like this. Just imagine that way. And once you leave this rubber band, what will happen? This bump will travel forward. So this bump is traveling forward, let's say with the speed of v wave. And this shape of this curve is y is equal to f of x. Again, remember y is like a property at different points. So if you take this as 0, 0, and this point will be f of 0. That's your height there. This is the scenario at t is equal to 0. That means this bump here or this disturbance is traveling forward with a speed v wave. After time t, this bump would have moved forward and you would have got it like this. So what happened here? This point here got shifted by a time of vt comma 0. So you're shifting your origin from 0 comma 0 to vt comma 0. You're getting it? So this bump is traveling forward with speed v in time t. What will happen? The bump ka middle part will travel a distance of vt, isn't it? So the peak value will go forward. You're getting how is this thing like? If I had to give an example, think of like this. Let's say in your classroom, right? There's one person there who is sitting on the floor. Another person, right, is just kneeling down. Another person, right, is, let's say they're just sitting on the bench. And another guy is standing. And the other guy is again sitting on the bench. And the other guy is kneeling down. And the other guy is sitting on the floor. So we have people like this. Just a crude example. You're getting it? So we have 1, 2, 3, 4, 5, 7 people there. So this guy is on the ground, this guy is on the ground, these two are kneeling down, these are sitting on the bench, and this guy is standing. If you just connect all their heads, it would look something like this. Okay? This is the scenario t is equal to 0. Next moment, what happened? This guy who's sitting here, he stood up a little, he started kneeling down. This guy who is kneeling down sat on the bench. This guy who's sitting on the bench stood up. This guy who is standing sat on the bench. This guy who is sitting here, he is kneeling down. This guy started sitting on the floor, and this guy actually started kneeling down. So, for a person who sees this, it looks like what? It looks like this whole chunk of people, right? They simply got shifted forward, isn't it? This guy has come here, this guy has come here, this guy has come here. It gives you an illusion as if everyone has gone forward by 1 unit. Now, same thing. If I join all the heads, what will you see? This is how the pulse will be. This is how the pulse will be. It feels as if the peak value has moved forward. Are you getting this? But in reality, no one has actually moved from anywhere. Everyone is standing at the same place and going up and down. But for a person who's seeing this, it gives you an illusion as if the whole thing is going forward. Something similar is happening here. So when I say this Y property, right, if you take like a string, this is all the heights of the particles. Next moment, the person at the peak value, this guy is coming down, this guy is going up, this guy is going up, this guy is going up, and these guys are coming down and coming down. So the picture looks like this. So think of that way. Technically, no one is going front and back. The pulse is going forward. It gives an illusion that way. What will happen to the new equation? Shifting of origin. So we have to shift the origin from 0, comma 0 to Vt. So this becomes f of x minus Vt. This is called a right traveling wave. So this is by shifting of origin. Because when I put x is equal to Vt, I should get f of 0 here. Because the peak value still remains same. This is shifting of origin. So if the wave is going forward, the wave equation will be f of x minus Vt. That is the general form. This is a right traveling wave. Suppose if the wave is traveling backward, this can be a little confusing. So this is the bump. This bump is traveling backward. This is the at t is 0. It's like you're taking a photograph. After some time, if you take a photograph, this bump won't be there at the same place. This bump would have moved a little forward. Now, if I ask you this question, where was the particle at the origin? At origin, this particle is here. At origin, now the particle is here. The particle is still there at the origin only. The height of that particle has decreased. But it gives you a feeling as if the whole thing has moved forward. So you have shifted your origin to minus Vt comma 0. So if a wave is traveling backward, again, shifting of origin, the equation will become y is equal to f of x plus vt. So the plus in the middle indicates it is a left traveling wave. So this is important, everyone. So this is our first thing. So a wave is represented mathematically f of x plus or minus vt. Let's try to understand what it means. What is y here? Y is a property. What property? It can be anything, pressure, displacement. This property is changing with x and the time. It is changing with two quantities. Property that changes with x and t. Let me give you one more crude example. What do you mean by it is changing with x and t? For example, let's say I'm looking at all of you, okay? If I ask you this question, right, where is your right hand? If I just ask this question, where is your right hand? What is the answer? The first thing you should ask, sir, whom are you talking about? Isn't it? There are like 20 people here, everyone right answer at different position. First, I need to ask you, boss, which person am I talking about? That is your position. Then I will say, okay, person A. Okay. What time are you talking about? Do you want the position of the right hand now, or 1 minute back, or 1 hour back? You get the point there? So if y, again example, if y is the position of a right hand of a person, then I need two things to tell you what is y. Who is the person and what time? Is that making sense? The same way, when you see a wave, what is y? Property of a particle. So the question is, which particle are you talking about and what time are you talking about? So it's like asking when a wave is going on a string, what is the displacement? I said, whose displacement are you asking? Which particle displacement you want and what time you want? I hope that is making sense. So that's the meaning of that equation, which has two variables, x and t. So the plus sign indicates, negative indicates right traveling wave. So keep that in mind. We can also write this in a more general form. F is equal to ax plus or minus bt. It should look in that form. So negative in the middle indicates it's a right traveling wave. So if the wave is going to the right, you get x minus vt. If you get a plus in the middle, it's a left traveling wave. This is also called as a progressive wave. So a progressive wave is a wave which goes in one direction. It doesn't turn back. Don't worry, we'll see more examples on this. You will get the hang of it. But for now, just understand that. I mean, if I talk a little more on this, again, you can't study a particle with both x and t at the same time. So if we keep time constant, so look at this. If I want to look at all your right hands at the same time, what should I do? I should take a photograph, right? If I take a photograph, I can see all of you at a given time. So if I keep time fixed, what you're seeing is the photograph. We are looking at all points at the same time. So everyone is at different positions. So what I'm seeing is a fixed positions at a given time. So when you keep time constant, you're looking at a photograph. This is important, like to understand like what happens when you keep something constant. If we are looking at all points at same time. So a y-x graph is actually a photograph. So when someone says this is a y-x graph of a wave, what he is giving you indirectly is a photograph. So a string is moving and someone takes a photograph. Maybe we have particles like A, B, and C. So y-x graph is a snapshot or a photograph. And just an example, see, let's say this is the time 0. And let's say this wave is going forward. Next moment, you know how it looks like? Since the wave is going forward, just push the wave little forward. So it becomes like this. See what happened. A is here. A is still on the same origin, but it has come down. B used to be here. Now B has gone up. C used to be here. C has come to the lowest position. So A, B, C are still at the same position, but they're going up and down. So after some time T, A is coming down, B is going up, and C is still going down. So what you're looking is the photographs. So you're taking photographs at different times. It would look like this. This is important. Like I said, right? Giving a formulas is easy, but you need to really feel like, oh, this is what is happening. Once you understand it, it becomes a little better. So is this. So there, this thing which I just showed you, so much lag. It's zero thing. Na? So see, so this is the slinky. Now see what it did. I just kept it on pause. What you're seeing is the position of a string. So that is a bump which is traveling forward, right? If I just off and on again, there. I just switched off and I kept it in pause again. Did you see the bump ka shape changed? The particles are not going front and back, but the bump ka shape is continuously changing. It is going forward. Look at this thing. So this is the shape of the string. So when I pause, you're looking at all the particles at a given time. This is a y-axis graph or position of all the particles. Now, if I again start and pause in a small time, see what happens to the shape. There. I on and paused it. See the shape, how it became. So this is the position of this thing at some other time. Again, if I pause and switch it off, again it changed. It keeps changing continuously. So that that's what you're looking at actually. When you're fixing the time, you're looking at all the particles at a given time. You're looking at the photographs. I hope that made little clear. And so the equation, right? That's what it means. The same way, if you keep x constant, you can't study both at the same time. So we need to fix at least one at a time. If you keep x constant, that means you're looking at only one particle. We are looking at one point for all times. So to put it in simple words, right? If I want to see all of you at the same time, I have to take a photograph. But if you want to just look at one of you, I can just keep looking at you for all times. I can't look at all of you at all times. I hope that is making sense. I cannot look at all of you at all times. If I look at one person, I can't see the other person. If I want to look at all of you, I have to take a photograph. That is the only way I can look at all of you at one time. We are looking at one point at all times. So if someone gives you a YT graph, so even though the graphs look same, so here the particle is basically going, A is going up and down. So it's like Y is equal to A sine omega t. You're drawing an SHM basically. You're looking at this particle motion which is going up and down. This is a graph. Okay with this? That's a bit about this thing. So that can be a little weird, but yeah. The next thing, this is an important thing. Now, every equation can't be a wave equation. They have to satisfy certain conditions. A wave equation has to satisfy three conditions. There, Arya has sent something about waves. I'll post it in the group. You guys can check it out. I think it's a wave generator or something. Yeah. So first condition, it should be in the form of, these are important. So this will be our first numerical. So listen carefully. All that introduction and theory is to get to this. And this is one of the most neglected part. Everyone goes to wave speed and all that stuff, but mathematically, right, these things are a little different. So it should be in the form of f of ax plus or minus bt. They should look in this form. I can just take out a common, then this will become x plus or minus b by a t. So this is looking like x plus or minus vt. So wave speed is given by coefficient of time by coefficient of x. B by a. Example, let me show you how they can frame it. They will say like this. A wave equation is given y is equal to e power minus 2x plus 3t whole square. This is a wave equation. And they'll ask you find the wave speed. So this wave is traveling. So coefficient of time is 3 by 2. And look at the middle, there is a plus sign. Plus indicates it is traveling on the left side. This is a 3 meters per second left traveling wave. If it is 2x minus 3t, it is a right traveling wave. How this looks, we will see later on. So I can draw actually. This thing will look like this. If you put a yx graph, look at this thing. If I put x0, t0, I will get a bump in the middle. If I put t infinity, you will get 0. This is the thing which I was actually drawing. So this is the bump. This is the shape. And this bump is traveling backward with 3 by 2 meters per second. And the height of this bump is 1. So that is the shape of that wave. So this is the first thing. It should be in the form of x plus or minus vt or ax plus or minus bt. Same thing. The second condition, f of x minus vt, I'll take a simpler version, but do partial differentiation, dou y by dou x. This would be f dash x minus vt. If you differentiate the inside, you'll get 1 anyways. Double differential dou square y by dou x square. So I hope everyone remembers partial differentiation. F double dash x minus vt. Next time, differentiate with time. Because this is depending with two different quantities, I can differentiate separately. Dou y by dou t will be minus v f dash x minus vt. Hope you remember chain rule. Differentiate this and differentiate whatever is inside. You get a minus v outside. Double differentiate dou square y by dou t square. This will become v square. This is v wave. F double dash x minus vt. You get a pretty nice equation. If you take the first two and equate it, we get a dou y by dou t is minus v wave dou y by dou x. Means if I replace this here, what is dou y by dt? V particle. If y is the displacement, this is the relation between particle speed and wave speed. A very important formula. Most people don't remember this. So this is the relation between a particle speed and wave speed. Quite a useful result. The second condition, if you equate the double differentials, dou square y by dou t square is equal to v square dou square y by dou x square. The double differential must be satisfied. What it physically means is this. The wave equation must be continuous and differentiable for all points. Why should a wave equation be continuous and differentiable? Just imagine, can you have a wave which is here, suddenly it vanishes and suddenly appears from here? You can't have a discontinuity in a wave. And if it is not differentiable, means your velocities are not same. The waves will break. You can't have such kind of waves. The function should be continuous and differentiable. Indirectly, that's what it tries to tell you. Function should be continuous and differentiable at all points. That's the second point there. The third one, the function should be finite for all x and t. No matter what value of x and t you put, it should never go to infinity. If someone satisfies all these three conditions, then it is a wave equation. So this is a bounded function. There. So these are the three things you need to satisfy. It should be in the form of f of x plus or minus bt, ax plus minus bt. It should satisfy the double differential. Generally, if you satisfy the first one, second gets satisfied. Third thing, the function should be finite and continuous for all x and t. Maybe I can just put everything together here. This is a good relation between wave speed and particle speed. Clear with this? Now, I'll give you a bunch of equations. You have to tell me which one is a wave and which one is not a wave. So let's see our first question. Which of the following is a wave equation? So if it is not a wave equation, you have to tell me which condition it doesn't satisfy. There, 10 of them. Take a minute, think about it. So let's see. The first one, it is not a wave. Q, if x is infinity, the function goes to infinity. It is not bounded. Like I said, no matter what value you keep, even if you keep infinity, should not go to infinity. If x is infinity or t is infinity, y tends to infinity. It doesn't satisfy the third condition. This is unbounded. Sine function is bounded, continuous. Yeah, this works. It looks like f of x plus minus vt. Cos square also works. You can write it as 1 plus cos 2 theta. There's no problem. Fourth doesn't work. Why? Tan 90 is undefined. It will go to infinity. What about E? E is a good one. You see E, right? People generally think like, sir, this can be written as x plus vt and x minus vt. Now be careful with that. The meaning of x plus vt, x minus vt is this. If I replace x plus vt with some variable z, I should not see x and time anywhere. But here you have both x plus vt and x minus vt. You cannot have both in the same function. You cannot separate them. If I put x plus vt as z, x minus vt will still remain. Right? We cannot have x plus vt and x minus vt together. When you have a still doubt, right, the best way to check is the second differential. So when you're confused about whether it is still or not, then you have to do the second differential and check. But the simplest way to check is this. If you replace x plus vt or x minus vt with a z, you should not see x and t anywhere. So this is gone. This is also gone. This will go to infinity, unbounded. If 2x minus 3t is 0, y will tend to infinity. G is okay. Because if this goes to 0, you still get a finite value. If this goes to infinity, you'll get a 0, still a finite value. This guy is also gone, unbounded. E power infinity is infinity. This is okay. So I did two things. I kept a minus here, I kept a square here. So it is always e power minus positive number. Ln 0 is undefined. So 1, 2, 3, 4. There are 4 wave equations in this. Yeah. All clear with this? So you have to satisfy those 3 conditions. Let's see one more. We have a wave equation 5 by 2 plus 3x plus 2t whole square. This is a wave equation. Find amplitude, wave speed, and plot yx graph, basically the shape of the string, the photograph, at t is equal to 3 seconds. Most of the time we will just stick to sine waves and stuff. So that's what we'll be studying in general, but they can still ask you questions like this. These are just based on wave equation. How do you find amplitude? Remember the definition of amplitude, the maximum displacement from the mean position. So they're asking maximum value of y. When do you get maximum value of y? If you put x is equal to 0, t is equal to 0, y ka value is maximum. The denominator, when it becomes minimum, so that means if the square function is 0, you get a maximum. So this is your amplitude. So the peak value is at this. What is the wave speed? Coefficient of time by coefficient of this. Minus I cap. Why? It is a plus in the middle. It is a left traveling wave. Let's try to draw the shape. Whenever they ask you to draw the shape, always first draw at 0. At t0, see how will this look like? At t0, if you draw a yx graph, t0, x0, that is the meaning of this. x0, t0, the bump is 5/2. Yeah, this is the highest value there. As x increases, the function decreases. As x becomes negative, even then the function decreases. So this is how the wave is. Bump in the middle, and it is going to infinity, 0 at infinities. And this bump is traveling with 3/2 meters per second, 2/3 meters per second. And now you're asking, find the shape of this pulse after 3 seconds. After 3 seconds, this bump will travel how much? 2/3 into 3, 2 meters. So basically, you have to push this whole bump left side by 2 meters. So this will be -2, comma 0. This coordinate will be -2, comma 5/2. And this bump is traveling backward. That is the answer at t is equal to 3. Is that making sense how to draw the shape? First draw at t0 and then just shift the bump by whatever distance it traveled. So if you put t0 here, this function will be y is equal to 5/2 plus 9x square. You can clearly see x0 it is maximum, x infinity and minus infinity it is becoming 0. So this is a function which is decreasing on both the sides and increases at the center. All clear with this? This is how they'll frame questions on wave equation. Some reason it is lagging a lot today. There are good things I wanted to. This is another website I have. See, this is a link I'll send you. This is a PHAT. Okay, so there you can see there is a wrench kind of thing and there's a the beat kind of thing. This is a wave. So if I move this on the left and right, so there I can generate waves. So if I move it faster, I get waves. If I move it slower, so I can put it in slow motion here. And if I move it, can you see how the pulse is traveling? So there, see how the pulse is traveling there. If I pause it here, can you see the bump? This is what I was saying. The bump is traveling forward. And look at the red color beads, okay? None of them go front and back. They're actually going always at up and down only. Can I draw that ruler? Reference line. I think ruler I can do this thing, I guess. This is a stopwatch reference line. So I can actually make it like a machine also. See, this thing keeps going up and down. I'll send you this link. You can play around a bit. You can generate pulses here. It's a decent one. So these things, right, mainly you need to see and visualize. Once you get the hang of it, it feels like, okay, this is what is happening. So I know standing waves will keep coming. So there, that's a bit about it. So what we did was just the intro of the waves and stuff. And this is the more mathematical part, what we did today. Right. In the next class, when we catch up, we will do few more problems on this, but we will not be studying these kind of waves in general. All the waves we study, we limit our study to very specific cases. For transverse waves, we study waves on a string. For longitudinal waves, we study sound waves. That's it. We study only these two. And we study all the waves generated by SHM sources. So your functions also will look good. So next class, we will do that. And then we will also do something called wave speed and stuff. But yeah, the overall chapter, you will find it is not really that weird, except for little bit of a theory today and this equations. Okay, but ray optics is done. Like I keep saying, you have a deadline. Do finish your ray optics by next week. And then waves, I think after next class, you can start doing even waves also. If you're doing HCV, waves are 2 chapters in HCV. Sound waves is different. Waves on a string is different. We will finish off waves on a string in another 3 classes. So you'll be able to do it. Okay, with that, we'll wrap up for the day. And do remember, there's a test online tomorrow. So make sure to give it. So I'll see you guys again on Tuesday, same time. So any doubts, anything else, please stay back or